So guys saw different types of telescopes. So you will be learning about how refraction and magnification happens in a refracting telescope. So this is how a telescope looks like. So what we have is we have an objective lens. So this is the objective lens, and Priyanka did it till here. So you guys saw how the magnification and how an image is formed in different types of telescopes. So now you will be studying about a refraction or refracting telescope. So what you guys are seeing is a refracting telescope. In this, what we have is this is the objective lens and this is the eyepiece. Now here, one very important thing is the objective lens is very big. So bigger the lens we have, better the image quality we can say. And you have the eyepiece. Now what we have, see one important thing, the light ray which is coming here, see this is the light ray which is coming. So all of them will converge to a point. So here we have A dash, B dash, and that A dash, B dash, see this point is, we can call this as FE. This is the principal focus for the eyepiece. We have A dash, B dash, which is between C dash and FE. So a virtual image will be formed, which is nothing but A dash, B dash. Okay, so here what we have, this is an inverted image and A dash, B dash is a virtual image. Since we are talking about heavenly bodies and most of them are circular, it's not gonna matter whether it's inverted or not. Now, the light rays are coming from infinity, right? And all of them will come and it makes an angle alpha. So this is angle alpha. If this is angle alpha, then even this will also be alpha because vertically opposite angles. Then what we have is we have this angle to be beta, because A dash B dash is subtending an angle beta, correct? So this is beta. Now what we have, see, first we need to know what is the magnification power for a telescope. How we can define is, it is defined as the ratio of the angle subtended at the eye by the image formed at the least distance of distinct vision to the angle subtended at the eye by the object lying at infinity when seen directly. So in other words, what it tells you is, see, the angle subtended at the eye by the image form, that's basically beta, and to the angle subtended at the eye by the object lying at infinity. The object lying at infinity is making an angle of alpha, correct? So again we come up with the same thing, that is, we have m is equal to beta divided by alpha. We have the same thing. Since beta and alpha are small angles, we can replace beta and alpha by tan beta divided by tan of alpha. This is what we get. Now again we have to take the tan. So what we'll consider is, see, here we have alpha, so we take C A dash B dash. Okay, so let's try to do that particular derivation. Now what we have is, in triangle C A dash B dash, as you can see, tan alpha becomes A dash B dash. Tan alpha becomes A dash B dash divided by C A dash, correct? Then we have to figure out tan of beta. See, in tan beta, again what we do is we take triangle C A dash B dash itself. Okay, so I'm sorry, we have to take C dash A dash B dash, not C A dash B dash. So in triangle C dash A dash B dash, we have tan of beta is equal to A dash B dash divided by C dash A dash. So this is what we have. Okay, now if you substitute that, we have m is equal to A dash B dash by C dash A dash divided by A dash B dash divided by C A dash. These two gets cancelled, so we end up with C A dash divided by C dash A dash. So we have M is equal to C dash A dash, C A dash divided by C dash A dash. Okay. Now, by Cartesian conventions, so what we have is C A dash is nothing but the focal length of the objective length, which is positive, and C dash A dash is the C dash A dash, basically it's the object distance for the eyepiece, and it is in the negative direction, correct? So what we get, so this will be nothing but F naught divided by minus UE. So this is what we have. So we get M is equal to minus F naught divided by UE. Okay, so this is what we get. Now we have to use the lens formula, which is minus 1 by UE plus 1 by VE is equal to 1 over FE. Okay, now here UE is negative, correct, and VE is nothing but minus D, which is that A dash B dash distance, right? So what we'll get is minus 1 over minus UE plus 1 over minus D is equal to 1 over FE. So this is what we get. In other words, we can also write this, see, this will become positive, correct? So we get 1 by UE is equal to 1 by D plus 1 by FE. So this is what we get, right? Now what we'll do is 1 by FE, we'll take it common, meaning 1 by UE is equal to 1 by FE into 1 plus FE divided by D. Okay, so this is what we have. Now, see, 1 by UE, we can substitute in terms of M, correct? See, if you look at this, 1 by UE is minus M by F naught. So, meaning, we can represent this in terms of magnification, right? So, when you do that, you will get the answer as M is equal to minus F naught by FE minus F naught by FE to 1 plus FE divided by D. This is what we get. So remember, at the last what we did was we took this value, that is 1 by UE, in terms of magnification. Okay, so that's how we get the minus F naught. So we have M is equal to minus F naught by FE into 1 plus FE divided by D. Now this is the magnification produced by a refracting telescope.